Okay, so we have the escape velocity from the moon is much smaller than from Earth, and it gives us the values 2.38 kilometers per second. At what temperature would hydrogen molecules, and it gives us the molar mass is 2.016 grams per mole, have an RMS velocity equal to the moon's escape velocity. And for the people listening to this recording, that's probably just the two of you when you go home. I made the changes there. It's not the average velocity. It's a different thing. And so I just set the V escape is equal to V RMS, consistent with what the problem asked. And they give us the V escape is 2.38 kilometers per second. Now, is that what I'm going to write down? No. Why not?
Because we need it in meters?
Yeah. So I'm just going to use 2,380 meters per second. It's the same thing. So we just solved that for temperature. So do it.
So we'd square and then we'd multiply over the m and divide by 3r.
And what is the value for R? You don't have that equation sheet.
I don't have it either.
And you'd think that me as the teacher would have something like this memorized, but .314 joules. 8.31. Yeah. I should have stuck with the first one I saw. This had, it did have, the first one had the units I wanted. 8.314472 joules per Kelvin times mole. So I have one more thing I'm going to have to take care of. Grams is not the standard unit for mass, right?
It's kilograms.
It's kilograms. So I'm going to have to do a conversion of, I'll change the color here, times 1 kilogram per 1,000 grams.
Please. Thank you. Yeah, that's perfect. I can see that.
So Nice is punching this into her calculator. We better get a temperature that's reasonably low because the moon has no ability to hold on to hydrogen gas.
457.
Now, we only have 3 significant digits, so that's going to be 458 kelvins. So, 458 kelvins. Think about that temperature. Is that a high temperature or a low temperature?
Isn't that high? Because 273.15 is... Oh, that's 0 for
Celsius.
For Celsius. Yeah, so that's 258. No.
It's just 2 Celsius.
It's 185 in Celsius.
So 185 degrees Celsius.
That's high.
185? I wrote my 3 and 7 backward. Okay, yeah, I believe you.
Oh, yeah, okay.
Okay, so that would be a relatively high temperature. And yet it can't hold on to any gas. You know why?
Because it's hydrogen.
When the sun is shining on the surface gets hot. And so the gas gets hot. and you have a large percentage of the gas can escape. Even if it's not the RMS, even if the RMS speed is less than the escape speed, a large percentage is above that. And so a large percentage gets lost when the sun is shining. Now, when the sun is not shining, it gets really bitterly cold, and it would be able to hold a lot of gas then. But when it's hot, even though that's a high temperature, that's much higher than the average temperature on the moon. In fact, let me check what the hottest temperature on the moon is. Temperatures on the moon are very hot in the daytime, about 100 degrees Celsius, right? So that's in the ballpark of 185.
So the concept for this one is gas law.
Yeah, it's
Ideal
the kinetic
gas.
theory of gases. Right, the kinetic theory of gases means we're relating the kinetic energy to the temperature.
Means that we're connecting. Kinetic theory to the gas law, you said?
We're relating the kinetic energy to the
to the temperature of
Temperature.
gases. Okay. Thank you.
You know, I could tell as soon as I started that it was going to crash. I don't know what was. It's like the whole screen turned white when it shouldn't have. Do I have a spreadsheet open? I don't think I do.
I don't even know what to tell you.
We just know that it's Microsoft's fault. You can't make software that doesn't crash. Or maybe it's my fault. My phone's been crashing ever since I started the beta testing. And from iOS 11, like before it was ever released, beta 4, my phone's been crashing, and it continues. I'm on now 11.2, like release 2 or 3, it's still crashing. It's crazy. I've submitted about 10 bug reports, and I must be the only one because Apple shows absolutely no interest in fixing it. Okay, I'm going to open up a spreadsheet, put a little stuff in there, definitely not save it. That's our new trick to make Microsoft behave.
Flow rate.
That's weird.
Flow rate. How do we figure out flow rate again? Q is equal to flow rate.
Uh-oh.
Area
I don't have a good feeling.
and pressure.
That could have worked.
Pressure.
Dun, 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 dun. Dun,
Okay.
Okay, this is the one you want to do, right?
Yes, please.
Blood is pumped from the heart at a rate of 5 liters per minute into the aorta of radius 1 centimeter. Determine the speed of blood through the aorta. Okay, this one is very straightforward. And as soon as it comes up on this, I'll start working on it. Trust me, it's coming. I'll just start right. There we go. Okay, so we know the flow rate is equal to the speed times the area.
Oh, yeah. Okay.
And so we have aorta of radius 1 centimeter. That's pretty much, well, no, radius 1 centimeter. I made my diameter 1 centimeter. Here's our aorta to the best of my drawing ability. So in this equation, the flow rate is VA. What's the area going to be?
pi r squared.
Yes. So we have Q is equal to V pi r squared. This is not very hard. What is V?
5 liter per minute.
Well, solving this equation.
Oh. So Q over pi r squared.
5.0 liters per minute over pi times 1.0 centimeters quantity squared. And then we have a lot of converting to do. Because those aren't standard units. I'm not going to get an answer in standard units here. So if I multiply that through, I'm going to have 5 over pi. What's 5 over pi?
1.5 now.
And looking at my units, that's liters per centimeter squared minute. That is so unfulfilling to write down. That's my speed.
Did you really go anywhere?
So how do we convert that into something that's meaningful?
Change centimeters to meters. Change minutes to seconds.
Okay, I'm going to start with the second one you did. Minutes to seconds.
There's 60 seconds in a minute.
Okay. Now, what is a liter?
10 to
It's
the third of
it's
centimeter
1,000
cube.
something. 10 to the
1,000 milliliters,
cube.
and a milliliter is a centimeter cubed.
Yeah.
So it's 1,000 centimeters cubed per liter.
Yeah.
Now, if I do this, I'm going to cancel 2 of these centimeters.
Mm-hmm.
You can't see where I'm hovering. I'm going to cancel 2 of these with 2 of the centimeters in my centimeters cubed. So I'm just left with 1 centimeter. And so for my conversion of distance, that's why I saved it to the end. I'm just going to have 1 meter per 100 centimeters. And so now if I look at my units,
Meter per second.
I have centimeters squared times centimeters cubed, and those all canceled out. And then my liters canceled, and my minutes canceled. And now I'm going to have it in meters per second.
Pi 2 6
Maximize it, please.
Yes.
Thank you. Thank you.
I will, of course, just blame Microsoft and
Okay,
not take any of the responsibility on my own.
got it.
Okay. Yep, that's the right answer.
Per liter. Yeah, and then 1 meter is equal to 100.
And we only have 2 sig figs, so 0.27 meters per second. Now, oddly enough, they actually have their answer in centimeters per second. So we didn't have to have that last conversion in red if we wanted it in centimeters per second. But I wanted it in standard units of meters per second.
Okay.
Because I'm old school that way. Now, living life on the edge. Yep, living life on the edge. Good thing we protected ourselves.
I don't understand.
Come on. Cancel. Boom. Don't say. So frustrating.
This one is flow rate and relation to velocity.
Ah, okay.
Next one is Archimedes.
Principle.
Okay. Archimedes' principle can be used to calculate the density of a fluid. This was on the test.
Mm-hmm.
Oh yeah.
Mm-hmm.
Can use to calculate the density of a fluid as well as that of a solid. Suppose a chunk of iron with a mass of 390.0 grams in air is found to have an apparent mass of 350.5 grams when completely submerged in an unknown liquid. So basically, I'm going to draw a figure that shows the mass in air.
We did this one with Ashley.
I'm hanging it by a string, and I have a force of tension up, force of gravity down, some of the forces in the vertical direction, so I'm going to define y as my vertical direction, equals mass and acceleration, which is 0 because I'm just hanging it there. And I have the force tension is equal to force of gravity is equal to mg, which doesn't really help me, but gets me started along by solving. Now I put it in a beaker that's filled with some unknown fluid. Apparently it's a pink fluid. And so it's in here, and I'm hanging it again by a string. And so my forces are going to be force tension, force gravity, and force buoyant. Some of the forces in the y direction is equal to force tension. I better put force tension prime plus force buoyant minus force of gravity equals 0 because it's, again, in equilibrium. And now we look at what we know. We know that the force tension prime is the apparent mass times g. Right? How do I know it's the apparent mass times g? Because that's what it means for the apparent mass. That's how much it appears when I put it on a scale in the fluid. So the force tension prime is the apparent mass times g, and then plus force buoyant minus the force of gravity, which is the actual mass times g, is 0, which gives me force buoyant is equal to mass minus mass apparent g. That was really pretty obvious. But what is the force buoyant? Now we're going to start to what actually most people basically started here in solving the problem on the test. What is the buoyant force?
Density times volume.
Density of what?
Of the object.
Density of the fluid times the volume displaced times g. Now there's an obvious thing to do. I have a g on both sides, so let's cancel that g. And I'm looking for density of the fluid, so I'm going to divide everything by the volume displaced. And I have density of the fluid is equal to m minus ma divided by the volume displaced. What do I not know in this equation?
The volume. Well, we don't have the volume that was displaced yet.
Yeah. But we do know it's submerged.
So we can take the subtraction of what it was in the air minus what it is in the water.
Well, we don't have volume measurements.
Oh,
but we know that the volume displaced has to equal the volume of the iron. I used I for iron. I could have used Fe for iron, because it's completely submerged. And furthermore, we know that the volume of the iron is equal to, just by the definition that rho is equal to mass over volume, then volume must be mass over rho. I'm going to use Fe instead of I. I just changed my mind. So I'm going to combine these two ideas. So now we just put in our values. So we were given that the density of iron is 7.8 grams per centimeter cubed. Times 1 minus the mass apparent was 350.5 grams over the actual mass 300. Oops. One of those is wrong. 350.5. Okay.
Zero percent.
That's a 9. And as we said before, that suggests that this might be ethanol. Is it possible to get another fluid that has the same density? Yes. So it's not a definitive test. It's suggestive. Questions? Shall we move on? Go to the next one?
Mm.
Look what my grandson gave me for my birthday. Isn't that nice? Sure, if you insist.
I was reading it.
Oh, okay. I thought you were like, whatever. And you know what's super cute? My stepdaughter, she took dictation from my other grandson, his third birthday was a week before mine.
Okay.
And so I got a card that's, like just random words. It's so funny. Okay. New material.
Success in life.
All right, so we have a power plant is 52% efficient. Remember in class today, I talked about efficiency and said, we wish that we could have 100% efficiency, but the third law of thermodynamics says it's impossible to reach absolute zero. So clearly you're not going to convert everything thermal energy into mechanical energy. Mm-hmm. And furthermore, it turns out when we learn the thermodynamics, because you're going from a hot reservoir to a cold reservoir that's, very far away from absolute zero, the actual efficiency is far, far less than 1. So here it says a power plant is 52% efficient. That would be really good. And it produces 1.5 times 10 to the 13th kilojoules of work output daily. So I'm going to have work is equal to, okay, that's too high. It's going to be on top of this when it ever comes up. Maybe not. Work is equal to 1, excellent, 1.5 times 10 to the 13th joules in 1 day. Technically, that's a power, but we're just going to say that what is it for 1 day? And that's the work from the first power plant. A second power plant produces 1.7 times 10 to the 13th joules in a day. And we have different efficiencies for the two. The first power plant is 52% efficient, and the second one is 55% efficient. Now, at this point, we didn't go over this in class yet, and so we have to think about this logically. You can totally do this. It's not like it takes specific knowledge. If it is 52% efficient, what does that mean?
48% is lost.
Okay, so the efficiency is equal to the output. The output. What's the output of your power plant? It's the energy. It's the work.
Mm-hmm.
So the efficiency is the output, which is the work, divided by the input, how much energy you put in. So the energy you put in is the heat at high temperature. So we can go through this and we can immediately calculate that the heat at high temperature is equal to the work times the efficiency. But the question doesn't ask us what the heat taken in is. It says how much heat is released. And so we have to go to the equation we talked about just before, well, when you were here this morning, just before you left. That was, remember problem 2? For a heat engine, you cycle around, so the change in internal energy for one cycle is 0. And that gives you the condition that says that the work is equal to QH minus QL. That was, I think, problem 2 from SHW30. Maybe it was problem 1, but it was one of the ones we did this morning.
It had the change of energy, internal energy, which was equal to heat minus work. And then we had...
I went from there down to show why for a cycle where delta U is 0 for the complete cycle.
Energy is equal to work in this one because internal energy equals 0.
The change in internal energy is 0.
Yes, the change in internal.
So this equation has to be true for a heat engine or for a cycle. And so since this is a heat engine that's going over and over and over again, it's doing a whole bunch of cycles. And so that's going to be true. So now we have QH and we're given W, so we can find QL. QL is the heat at low temperature that's exhausted. Is QH minus W, right? You just take this equation that I underlined and rearrange it. And since QH is work times efficiency, factor out the work. Okay, where did I mess up here? Efficiency is the work over QH. That's right. QH is equal to work over efficiency. That's where I messed up. It's embarrassing that it's been that long before I realized I made a mistake there. So we can now calculate what QL is. So QL1 is equal to work 1 times 1 over efficiency 1 minus 1 equals 1.5 times 10 to the 13th joules times 1 divided by 0.52. If it's 52% efficiency, the actual efficiency is 0.52. What'd you get, Nice?
1.38.
Very close, aren't they?
Mm-hmm.
Okay, so we used here the definition of what efficiency means and the relationship between work and heat for a cycle in a heat engine to solve for the energy that was being released.
So it should be QL2.
Their answer rounds to one digit, and so it has them as the same. Or one digit rounds to 2 because we only have 2 sig figs. And so it has them as the same. And they are, to correct sig figs, they are the same. When it says which one releases more, you expect them to actually say this one or that one. But the answers are. Any questions, sir?
No.
Pretty straightforward? Yep. If you say so. No. Oh, no. We're not even close to this one. Carnot engine. Sadi Carnot came up with a heat engine that is the theoretical best, most efficient engine you can have. It's theoretical for a number of reasons. One of them is that in order for a Carnot engine to be real, it has to be running so slow that it's constantly in equilibrium, which means that the time it's going to take to do one cycle of the engine is infinite. Hence, it's not a real engine. It would take it. Okay, so the Carnot engine is using a Carnot cycle, which on the PV diagram is something like this. So these two that I did in green are, notice it says at TH and at TL. That means they're constant temperature, which we call isotherms or isothermal processes. So you have an isothermal expansion where heat goes in at constant temperature. So that's like, we saw the Hero engine picture in class. You have the fire that's burning at a constant temperature. And so the heat is going into the water at a constant temperature there.
Is that the machine, the thing that we saw earlier today?
Yeah, the Hero engine is the picture that I had in class that had a fire with
and
a
then the
vessel.
thingy on top that was real.
Yeah.
Okay.
So that's an isothermal process, constant temperature. So you have an isothermal expansion, constant temperature, heat is flowing in. And then you have these magenta ones are what is called adiabatic. That's not a word that's in most people's vocabularies.
No.
Adiabatic means no heat. Technically, the word is something like, no flow or something like that. But an adiabatic process is one where there is no heat flowing. So that's an adiabatic expansion. Then you have an isothermal contraction and an adiabatic contraction. So those 4 steps are the Carnot cycle. And you can show that this Carnot cycle gives you the optimal efficiency. And the efficiency for the Carnot engine is equal to temperature high minus temperature hot minus temperature cold all over temperature hot. So this equation here allows us to solve for temperature if we know the efficiency. So I had to introduce what the Carnot cycle is so we know what it's talking about. And then there's this relationship for the efficiency. Now remember, efficiency is equal to the work out over the heat in, right?
Mm-hmm.
And so the heat in is, of course, at temperature high. And it turns out that when you do the calculations, the heat is proportional to the temperature if you're on an adiabatic curve. And so that's why it comes out to have this relationship, because you have QH minus QC is equal to work. And since they're proportional to temperature high, work is proportional temperature high minus temperature cold. And so if I take the work divided by QH, then I have the efficiency. QH minus Q cold over QH is the efficiency. Mm-hmm. And then the proportionality is why it drops down to just TH minus TC over TH. So we're looking for TC. How do I solve this for TC?
Multiply by H and divide by H. But that doesn't make it. Oh no, multiply by H and subtract H.
So TC is equal to TH minus efficiency times TH is equal to TH times 1 minus efficiency. So what is TH?
About 450 degrees Celsius.
It is, but I'm not going to write that down.
In Kelvin?
Has to be in kelvins. Okay. Right, in the numerator there, TH minus TC, it would have been fine to use Celsius, but the denominator divided by TH, that's not a change, must be in kelvins. So I have to do the whole thing in kelvins. So 450 plus 273, 723. Times 0.3.
Oh, oops.
Two ones.
Whoa. Really? Oh yeah, I divide instead of multiplying. Okay, so I only have 3 sig figs, so 217. Okay. I looked and they have 217. I'm like, how is that wrong? 217 Celsius. How many Celsius is 217 kelvins?
217 minus 273 minus 56.
And that's, of course, the correct answer.
Okay.
Okay.
Thank you.
Our time here is done.
Mhm.